Maybe this will work. All right, well, I hope it's working. I guess we'll find out the hard way. So today's notes we're going to title these Breadboard notes. And in your box, or on top of your box, you'll find a thing that looks like this. Or maybe it looks like this. They come in different brands and varieties. And that thing in the box is, its affectionate name is a breadboard. And I'm thinking that it's probably, what I remember is it's named that because it resembles an old-timey piece of equipment that people used when they made bread. A board for making bread, a breadboard, and it was a board that had holes in it. So back when Benjamin Franklin was president, right, when they made bread, they used a breadboard. And so this looks like it. It doesn't really function at all like a breadboard for making bread at all, but it looks like one. It's got a lot of holes in it. All right. So the purpose of the breadboard it provides electrical connections for components. So all the things that we can use to hook together to make circuits, to make robots do what robots do, or to make televisions do what televisions do. Whatever it is that's electronic out there, your phone, all of it, they all have components in them that have different functions that are connected together electrically in different ways. The breadboards are just used for mock-ups. You're not actually going to find breadboards inside of things with things hooked in them. This isn't something that you would find in a robot, unless it was a really sketchy, that's the word I was thinking. I was thinking of a different word I didn't want to say. A sketchy robot maybe would have a breadboard circuit in it, but we don't do that. When we off camera, when we actually build things, we use green boards. And this is old technology too. This maybe is from some electronics back in the 70s or 80s. Current things like your cell phone's you're not going to find a green board in your smartphone that has all these big clunky things on it, right? This is probably an old television or an old computer or something, CRT tube board. But you can see it's got resistors on it. You can see resistors come in different colors, just like people. It's got capacitors. That's another thing. It's got these mysterious black boxes, which have integrated circuit chips in them. And so the green board, instead of the breadboard, is what you use to solder components together. The other class said that they were interested in learning how to solder, perhaps soldering together a little project this month. Is anybody in here interested in that? Or just Matthew then? Okay. All right, well, Matthew can do it then. Okay, James too? Just Matthew and James then. Okay. Sorry, I can't see anybody else. Anybody interested? No, nobody's interested. Pop quiz. Just kidding. Did we already do that pop quiz? You're saying, yeah, you're lying. I'm looking forward to the crinkly bottle sound showing up on my recording for the absent kids, Brian. So thank you for that. All right. So the breadboard's used for mock-ups. And in your kit somewhere, where they're supposed to be, but the other class put things away from me, so you know how that goes. They're supposed to be in either a cold beverage cup or a butter dish. So you should have 3 resistors located in there somewhere. And if we can't find them, we'll have to find them. I have more, but I'd rather not stop what I'm doing and go dig them out for you. So I'm hoping you all have your resistors. All right. So what I want you to do next is I want you to write down
the color code for the 3 resistors. So I'm just going to draw lines here. There's 4 stripes on each resistor. My resistors all have a gold band on one end, so I'm just going to write gold just to show you how I'm going to orientate my resistors so that the gold band is on the bottom of my list. All right, so just go ahead and see if you can figure out what those colors are, because sometimes it can be hard to tell what the color is. So let's see if we can all agree on what the colors are. And if you're a fast person, probably you can guess that the next thing we're going to do is use the color code to figure out what their values are in ohms. So you can move ahead to that if you are tired of waiting. But we'll wait for everybody to catch up. Write down the color codes. Does anybody need more time on this? I lose track of how much time it's been. Quietly raise your hand if you need more time to write down the colors. I'll wait. Yes, there is. I don't want to show you right now how many times. Okay, so I'm going to say that this one's color code is brown, black, black. And this one's color code is red, red, black. And this one's color code, so what are those colors? Definitely red in the middle. Sometimes this can confuse people. I happen to know, based on what this resistor is, because I picked it out, that this is supposed to be brown. If you thought it was violet, well, sometimes people think that, but it's not what it is. So now we're going to use our color code to figure out what the value of each resistor is in ohms. And I would like to remind you that the color code, we start with every stripe's color represents a digit. So we start with black, then we have brown, then we have the rainbow, except not indigo, and then we have gray, and then white. So we start with 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those colors represent. And I've always wondered why they picked them in this order, and I have a variety of theories, but currently what I'm settling on, maybe it just makes me feel good, is it's probably just cheaper to make black and brown stripes. You're going to find that these stripes show up on a lot of resistors, and maybe it's just cheaper to make black and brown stripes. Let's just go with that. Okay. Anyways, go ahead and use the color code to figure out what the value of the stripes are. What are they? Huh? Violet 7, yes. We don't have any violet stripes. Oh. Red and white. Great.
You're not going to go while I'm lecturing. Okay, so brown corresponds to 1. So the first stripe represents the number 1. The second stripe is black. It represents digit 0. And then the third stripe is black, which means I put 0 zeros on it. So it's just 10 ohms. A brown, black, black is 10 ohms. Red is 2. The second stripe is also 2. And the third stripe is black, which means, again, 0 ohms. Brown is 1. Red is 2. And now brown is 1, so how many zeros do I write after the 12? If it represents 1 0, I write down 1 0. So that one's 120 ohms. I chose these resistors specifically because they were close to the resistors we had in the worksheet yesterday on the simulation. And after we worked with the simulation for a while, I felt like there were a lot of holes in our knowledge base that the advanced circuit people assumed that we had. And I wanted to, the purpose of these notes is to kind of fill in a few of those holes, right? And also to show us what actually we're doing in the simulation. So in the simulation, we had a 10 ohm resistor, and we had a 20 ohm resistor. And actually, this is what the symbol for a resistor looks like. If you were a person that drew schematic diagrams and drew out circuits, that's what a resistor looks like. And then they said, let's stick an ohm meter on it and measure the total resistance. And we predicted that it was, this was 100. Right? Well, I got a 10. And the closest thing I could come to 20 was 22. I didn't have any 20s. And then I do have some 100s, but I decided not to use 100 because the stripe pattern on 100 is brown, black, brown, which is almost the same as brown, black, black. And my experience is that people get these resistors mixed up and they get put away wrong. So I thought I would just avoid that pain and sorrow that I endure when I have them both used at the same time and just give you a 120 instead. All right. So what I want to do is I want to show you how you would set up these resistors on this breadboard. So you're going to need to get your breadboard out. So there should be enough stuff for every 2 people to share unless you're sitting at a table by yourself. Then you get your own stuff. All right, so here's the breadboard, and this is how the breadboard works. I'll just pause for station identification while you locate your breadboard. Yeah. We're going to finish that thing after we do this. We're gonna spend our class time on that thing. I'm not going to make it be homework yet. So don't worry about it. It's not going to be. You're not going to get stuck with it over the weekend. All right. So the way that this works is, you can see that the breadboard has got a left and a right side. So the left and the right sides are separated. It's really two. It's a double. It's a deluxe breadboard. You have one whole set of breadboard over here. It's like 2 breadboards stuck together. In fact, you could actually buy them smaller than this so that it's just half of what this is. You could build 2 completely different circuits on the left and the right sides. Or you can use both sides together. The way that it works is on row 1, so if you look at your breadboard, you'll see that if your eyes are better than mine, that the rows have numbers. The rows are numbered. It starts at row 1, and my breadboard goes to row 64. So I have 64 rows. As a matter of fact, actually, I had told myself that I was going to use this breadboard instead, and I forgot. So now, you can see this is actually better. It's got, it numbers the rows 1, 5, 10, so this is 1, 2, 3, 4, 5. So every row is connected on the inside. It's like there's little tiny wires on the inside that connect these 5 holes together. Holes A, B, C, and D on row 1
are connected electrically with little wires. On the other side of the breadboard, F, G, H, and I are connected electrically, but the A, B, C, D, E's are not connected to the F, G, H, I, J's. Okay, these are separate. You'll notice on the side, whether or not you have this kind or this kind, that you have these rows on the side. These are different. All of the holes next to the red stripe are connected electrically, and all of the holes next to the blue stripe are connected electrically. And this is to provide electricity to the circuit. So you put the red lead in here for the positive voltage, and you put the other lead here for the ground or the negative voltage. And that just makes it so you can tap off of this. It's called a bus. This would be your positive bus, and this would be your negative bus. And you can just tap off of that into different places on your circuit to provide voltage. But we don't care about that today. All we care about is positions A, B, C, and D. So we're going to take the first resistor, and I just want you to copy what I do. In fact, I need to zoom in so we can see it a little bit better. So if we were going to actually build a circuit like we had in the simulation, we would take one lead, this is a two-lead device or a two-port device, and the legs are called leads. So we take this lead, and I'm going to stick it in row 1, right? And then I'm going to put the other leg really anywhere I want to except row 1. You cannot put it in row 1 because now it's just connected to itself. And I don't want to connect it to itself. I want to connect it to something else. So I'm going to take that leg, and I think it's just convenient for me to stick it over here in row 5 on the other side of the breadboard. So I've got one leg in row 1 and one leg in row 5. It doesn't matter what the letter is, as long as they're not in the same row. I could actually put this over here in row 1, and they're still not connected electrically, but I feel like that's just going to confuse people, so I'm not going to do that. It doesn't matter. Now I'm in letter E. I moved it. Oops, and now I'm not in row 5 anymore. All right, so now if I want to connect the 10 ohm to the 20 ohm, or 22 ohm in this case, right, I want these two to be connected like they're stuck together with wires. So I'm going to put both of them in the same row. If this is going to be connected to these two legs are going to be connected, they both have to be in row 5, and it doesn't matter which letter I pick. I can pick any letter, so I'm going to pick F. And now these are connected because they're in the same row. And again, I'm just going to pick a row. So I'm going to pick row 20. Now, as long as I don't put this in row 5, I can really put it anywhere as long as I'm just trying to sort these out. So they're connected like in the picture. And does anybody need help putting the resistors in the breadboard? Huh? The gray, the big gray cabinet has got tools. All the tools are in there. They're looking for helping hands. Okay. Anybody need help? You can ask the person next to you, or you can, claim you can have your own box. If you don't want to sit where you're supposed to, then just do it yourself in your own box. All right, so now I want to connect. Look at the picture. I've got the 10 connected to the 20, 22. And now I'm going to connect the 20 to the 100, but it's really a 120. And so I just need to make sure that these two legs are connected in the same row. So I put this one in row 20. And then I'm going to put this one over here in row 25. So notice that these are in the same row, and these are in the same row, and these two sides are open. And, all right, so this is an open circuit. It's not connected to any electricity. It's just this type of circuit. I've got to roll back out. Whoops, the other back out. This type of circuit is called a series circuit. So before we take any more notes on the series circuit, what I'd like you to do is get out your multimeter and measure the total resistance of the circuit. And I'm going to show you how. And I have to steal a multimeter from this team, and then I'll get it back. All right, so you have to remember that we're using ohms. Based on my wisdom and knowledge, I'm going to guess that a 100 and a 10 and a 20 are going to fit on the 200 scale. So I've got to find my 200 scale, and I'm not going to ruin the answer. So I'm going to move this over here. So I'm just going to put my leads, one across one side and one across the other, and write down whatever it says on the meter. All right, and then I'm going to give this to you so you can do it. You got 3 resistors? No. What is the resistor? Dude!
It's not my fault. It's my associate.
You didn't say anything, though. How are you going to get any pudding if you don't eat your meat? Right?
No.
Well, you don't get my cultural references. That's what you do have that one? Oh, Tom. All right. Keep going. We have one. Heartache. What's happening is there's a disconnected. All right. So when I measured it, I'm going to write down over here, what is the total or equivalent? Equivalent's really the word they like to use, because what it's saying is that there's a resistor I could pick out of the box, which is equal to all 3 of these together, and stick it in there, and just that resistor could do the job of all 3 of these. So when I measured it, I got 154 ohms. Again, just like last period. Did everybody get 154 ohms? I'm expecting you to say no.
We got 155.
We got 155 and a half. What'd you get? 165. Why are we getting different answers when we have the same resistors? And is it okay? Talk amongst yourselves. Why are we getting different answers when we all measured the same resistors? Yes, that's right. No, you're fine. So what I heard people saying was that the resistors, this stripe pattern says 10, this says 22, this says 120, but that doesn't mean these are what they actually are. The gold stripe means that these could all be 5% off of their values. So 5% off of 10 will be, it could be 9.5 to 10.5. This one, 120, could be 6 off either way, 126 to 114. So if my big resistor is 114 and yours is 126, we're not going to get the same answer. Some of your stripes are silver instead of gold. That's even worse, especially these 22 ohm resistors. A lot of them are silver striped resistors. All right, so for notes in a series circuit, we're going to say that the positive voltage goes to one end or one load. Right here, we can hook up the positive to here. The resistors are loads are the things that use electricity, and the negative or the ground goes to the other end. Every load shares a part, and if I go off screen, you got to tell me because I'm not looking up, of the voltage. Don't look up. I haven't watched it yet, so don't ruin it for me. I'm imagining everybody's a dumbass and they all die probably, but don't ruin it for me. All right. So in that type of circuit, which is a series circuit, the voltage, if we had a 9-volt battery and we stuck it across here, right, the voltage of that battery would be equal to the voltage across this one. So I could take my meter and measure this one's voltage, and this one's voltage drop, and these would all add up. Right, that the voltages across each load would add up, and the big resistor would get most of the voltage, and the little resistor would get the least amount of voltage, but they would all add up to 9. Minus a little bit that's lost because of wires and stuff. The current in this circuit is the same everywhere. That it's one loop. This is called a loop. And if I had a battery going in and out of here, the electricity would just flow through this loop around in a circle. So the current is the flow of electricity in a loop. And the resistors in this circuit just add up. R1 plus R2 plus R3. So these should have been 120 plus 22 plus 10. I should have got 152 ohms, but I got 154 ohms. But it's okay, because that's well within tolerance for those 3 resistors. It's only 2 ohms off for me. And now I'm going to give you a chance to catch up before I turn the paper over and finish the notes on the other side. Voltage of the battery. I like making my voltage symbol a little different than my velocity symbol, so I put horns on it, like it's some sort of team from Texas or something. Thank you. All right, if you need a little more time with the notes, can you raise your hand? Whatever volume you raise your hand. Battery voltage.
I see pencils wiggling. I'll wait.
Yes, all the current everywhere in the circuit. The current through this resistor is the same as the current through that resistor is the same as the current through that resistor. They're all connected in a loop. Like imagine a big canal of water, right? The flow everywhere in the canal would be the same at every point. Like this is the house, this is another house, this is another house on the canal. The water flows the same everywhere through the canal. We good? All right. So I'm going to turn the paper over and do the other side. And so on the other side, we're going to look at the other configuration, the other basic configuration for loads, or in this case, resistors. And when we do them like this, we call it parallel. So in the activity yesterday, they had a light bulb, and then they had a resistor, and then another resistor, and then there was other stuff, but I'm only going to care about the parallel part. So this is what it looked like, and they didn't look like this exactly because these are the actual symbols that people use for components when they're writing circuit diagrams, which is the way I do it. And in the simulation, they were just drawing little icons of, like a little cartoon pictures of them. All right. So I want you to see how it's different when they're in parallel. So we're going to take our resistors and pull them all out and build ourselves a parallel circuit. So I'll give you a second to get your breadboard out and yank your resistors out. Hello. Cool. Giddy heart! It's your daily slip of pinkness. Sorry, did I blast you? I'm sorry. All right. So on the breadboard, right, we have the rows that are connected, just like before. The breadboard hasn't changed. And notice on the drawing, I want all of the resistors to be connected on the top. All of their top legs or leads are connected, and all their bottom legs are connected. So what we're going to do is we're going to take this lead for the 10 ohm resistor, and we're going to put one lead in row 1, and then I'm going to put the other lead in row 15. I'm kidding. I'm going to put it in 10. And if I want both sides to be connected electrically, I've got to put both sides in the same rows. So I take my 22 ohm resistor, and I also put the top one in row 1 so that they're connected on the top, and I put this so that they're connected on the bottom. Just like that. And then I will let you guess how I'm going to put the third resistor in there before I do it. I'll give you a chance to do it first, and then you can fix it. How am I going to hook up the third resistor so that it's in parallel with the first two? Let me zoom in a little bit so we can see what's going on here. So hopefully by now you've realized, well, if they're all going to be connected like in this picture, this one also has to be in row 1, and this one also has to, and the other side has to be in row 10. So this is a parallel circuit, and they're in parallel. And now what I want to know is, what is the equivalent resistance of this circuit? Oh. Nope. So that's what I'm going to write down. I'm going to write down measure the equivalent resistance. Let's take our meter and measure what it is. I'm going to steal your meter. I'm going to measure it off camera so that you can't see the surprise. Right? But I'm going to put one lead on the top and 1 lead on the bottom. And what you're going to find is it doesn't matter which resistor I touch on the top and which resistor I touch on the bottom. It's always going to give me the same answer. And that's because, as far as the meter's concerned, it only sees one resistor. These look like one resistor to it. All right, I've got my number. So go ahead and measure your total resistance or equivalent resistance for these 3 resistors in parallel. Yeah, this is a wonky meter. Not the best, it's not the worst. That was my school motto in high school. Not the worst. Only shooting for 500. I'll go to state and make that season too long. Am I rushing you? Did you get it? Huh? Okay, so when I measured it, I got 7 ohms, and maybe you got something different. I think sometimes the issue is the meters. I may not have the right leads, or they have dead batteries or something. I got 7 ohms. All right, so in this circuit, the voltage of the battery is the same everywhere. If I hooked up a battery to these, to one side and the other, they would all get the whole battery. They would have the same voltage drop, the same potential. The current, though, is different through each resistor. The little resistor gets a lot of current, and the big resistor only gets a little bit of current. Right? So they each get a different amount of current, even though they all have the same voltage, because they all have different resistances. And the resistance is found with this funky addition of fractions thing that we looked at yesterday. I thought it would be worth going over again. So to find what so I got 7 on the meter. I'm wondering if that was close to the right answer. So I say that the 1 over the answer, the inverse of the answer, is equal to 1 over 10 plus 1 over 22 plus 1 over 120. Now I could find a least common denominator, some number that these all divide into, but I don't think that sounds very fun. Because it's not an easy one, right? Probably. So instead I'm going to decimalize these numbers. So what I'm going to do is, I'm going to say 10 inverse, oops, it's not on. 10 inverse is equal to 0.1. 0.1. 22 inverse. So to the negative 1 power is the same as saying 1 divided by. It's equal to 0.045 to infinity and beyond. And 120 inverse is 0.0833 to infinity and beyond. And that's all equal to 1 over the actual value. So now I'm going to add them together. And the nice thing about this type of calculator, if you have one, is I can just do this. 10 inverse plus 22 inverse plus 120 inverse. Boom, it's equal to 0.15378 to infinity and beyond. 0.15378. So that's not the actual answer. 1 over the answer is equal to 0.15378 over 1. To get the answer, I've got to flip those fractions so that it's r over 1 is equal to 1 over 0.15378. So again, on my calculator, I just hit the inverse button, and it says r is equal to 6.5 ohms. Well, I measured 7. Well, I think that's probably fine, because one of my resistors is this old 22 ohm resistor from back that's like 40 or 50-year-old resistor. Who knows, right? It's probably not that great. I think a half an ohm difference between what was expected and what was measured is probably pretty good. It's good enough. And those are the notes. I'm going to pick up the notes. You can either share your electronic notes with me, or I'm going to pick up your paper notes at the end of the period. But I'd like you to hold on to them for now, because I'd like you to spend a few minutes, or the rest of the period, on this right here. And you'll have to go to Canvas. So yesterday we finished up the first page, and we finished the second page. And now I would like us to work on 5 and 6, on question 5 and question 6. And I would like to go over the answers before the bell rings. So you're going to need to give me 2 or 3 minutes before the bell rings to show you what the answers are. So I have no intention of making you do this at home on your own. There's 3 pages of this left. I think if we get to the point where there's less than a page left, then I'll say, okay, let's just finish it at home. I'm done with this. But I don't feel like asking everybody to do 3 pages of this difficult assignment on your own over the weekend is very kind. So I'm not going to do that. But I would ask you to do 5 and 6 right now. And that's all I have to say about that. And I should have turned off the recording. So